Okay, welcome everybody to our 5.5 concept video, where we're going to talk some more about the normal probability density function, or the normal distribution, which I mentioned in the previous section. So we're going to focus on that a little bit more because it's really a special case. But before we do that, I do want to talk about some additional properties of probability density function. If you're working with a probability density function, you're looking at the probability of certain events happening. Well, it turns out that I can actually calculate the value that we would expect to happen, or the expected value for any given probability density function using integration. All I have to do is integrate over the entire domain, a to b, and just put an x in front of my probability density function. And that'll give me my expected value. So, for example, if I have a probability density function that measures wait time for a restaurant, how long do you have to wait? By doing this calculation where I put an x in front of my probability density function and then integrate it, I'll get the expected wait time. How much time should you expect to wait for this specific restaurant? And what's cool is I can think about expected value in a way such that this is really the same thing as your average value. It's just a different way to interpret it when I'm talking about probability. So your expected value and your average value are the same. Well, I can actually take this one step further. If I define e of x as this integral where I'm just adding an x in front of my p of x, then theoretically e of x squared would be the same integral, but I'm just multiplying an x squared in front. Why am I talking about this? Because I can actually calculate the variance of a probability density function using some similar calculations here. So the variance, which my symbol for that is this sigma squared, is equal to this e of x squared. So the same integration, just with an x squared in front of my probability density function, minus the expected value squared. Now, even though they both have an e and they both have a squared, these are two very different things. This right here is just the computation above, and then when you're done, you square the value. This is you adding an x squared in front of the p of x before doing your calculations. Once again, what this tells me is I can use integration to actually calculate the variance of a probability density function. What is variance related to? It's related to standard deviation. If you know the variance, all you have to do to find the standard deviation is just square root the variance. And then you have your standard deviation. So using integration, you can find your average value. You can find your standard deviation for any given probability density function. Now, keep in mind that for certain probability density functions, like an exponential density function, you're going to have to use integration by parts in order to actually find this integral. Same thing if you have an x squared in front. You're going to have to use integration by parts. In fact, you're probably going to have to use tabular integration by parts. The bottom line here is, using these formulas, I can use integration to calculate average and standard deviation for a probability density function. So now let's talk about the normal probability density function. It's commonly called the normal distribution. And I showed you a picture of this in the previous video. And if you remember, the domain of this function is negative infinity to a positive infinity. And it's centered around the mean of the data. Well, it turns out there's actually an equation that will model this line. And that equation is 1 over the standard deviation times the square root of 2 pi times e to the negative x, which represents your data value, minus the average or the mean squared over 2 times the standard deviation squared. Whoa, what an equation. Very complex, depends on a lot of different things. In fact, if you look closely, you'll notice that it depends on the average and it depends on the standard deviation of whatever data set you're working with. So in order to be able to create this equation, you need to know the mean and the standard deviation. But the other thing to realize about this equation is that it's impossible to integrate. Meaning I can't use all the concepts that we just learned in 5.4 in order to find my probabilities. So instead, what we need is a calculator. We need a high-powered calculator to do this for us. And so whenever you work with the normal distribution, you'll often see something like this. This is what's called a z-score table. And what it does is it finds a corresponding area for a given z-score along your x-axis. So if you find a certain z-score, it will give you the area between your mean, that center point of your data, and whatever z-score you actually have. That's what all of these numbers in the middle are. All of those numbers are areas. But what is a z-score? All a z-score is it's a way to describe how far your data value is from the mean depending on the standard deviation. So a z-score represents how many standard deviations a data point is away from the mean. If I want to express that mathematically, I can take my data point, find the distance from the mean by subtracting away whatever the mean is, and divide it by the standard deviation. And that gives me my z-score. Let me give you an example of this. Test scores are something that's often normally distributed. So let's say I were looking at student SAT scores. We could say that the mean SAT score was 1,150 with a standard deviation of 150. Now let's say you or someone you knew scores a 1,400 on the SAT. What I could do is I could find the z-score for that by doing 1,400 minus the average amount, 1,150, divided by your standard deviation, which is 150, and that gives you 1.67. I'm only going to keep 2 decimal places here, and I'll show you why. So now I can come look at the z-score table, and the left side of the z-score table is your ones place and your tenths place, and so I'm going to go to 1.6. And then the top of my z-score table is the hundredths place, so I'll go to 1.67 and find where those two things meet, and I get this 0.4525. Once again, this represents an area. It's an area between the mean and the specified z-value. So if I look at that graphically, that means that if I have this z-score of 1.67, then the area between the mean and that z-score is 0.4525. Well, how would I interpret that in this situation? I can interpret that by saying there is a 45.25% chance that someone will score between a 1,150 and a 1,400 on the SAT. Notice how it's in reference to the average, because that's what this area represents. It's between the average and whatever z-score you were looking at. Now, if you look at the table, there's only positive z-scores here. Does that mean negative z-scores don't exist? Well, of course not. What if instead you scored an 1,100 on the SAT? That's less than the average. If I plug that into my z-score formula, I get a negative 0.33. So a negative z-score represents a value that's lower than average. What do I do with the z-score table if it doesn't show me a negative 0.33? Well, an important thing to recognize with the normal distribution, an important property that it has, is that it is symmetric across the mean. Meaning the areas on the left side of the mean are the exact same as the areas on the right side of the mean. So if I want to figure out an area for this z-score of negative 0.33, I can instead just look at the area for positive 0.33. And I get this area right here. So that means this area between the mean and negative 0.33 is 0.1293. So the last thing to remember with a normal distribution is that because it's completely symmetric, if I wanted to know the area of one of the sides, so if I'm looking at the entire right side, how much area would that be? That area is 0.5. Why? Well, if I think about it conceptually, there's a 50% chance that you're going to be above average. And similarly, there's a 50% chance that you're below average. Numerically, the entire area is 1, and if I split it in half, making it symmetric on both sides, the area on each side is 0.5. So keep that in mind, because that'll come in handy with certain examples. So the last thing we need to talk about in 5.5 is percentiles. And what is a percentile? Well, percentiles represent another way to describe normally distributed data. So if you have your normal probability density curve, your bell curve, what a percentile does is it kind of does the opposite of what we just barely did. When we were looking at the z-score table here, what we were doing is we were looking at specific data values, finding their corresponding z-scores, and then using the z-score table in order to calculate certain probabilities. But with percentiles, instead of starting with the data points, I'm actually going to be looking for the data points that correspond to a specific area value. So for example, if I wanted to find the 25th percentile, what I would be looking for is I'd be looking for what data value or what z-score will result in me having 25% of the area, or an area of 0.25, below that value. That's what a percentile represents. It represents the data points such that 25% of all of your data values are below that. If you score in the 25th percentile, that means only 25% of all the test scores were lower than yours. If you score in the 90th percentile, that means 90% of the test scores were lower than yours. Well, how would I do that? Well, I would come right back up to my z-score table, and instead of having a z-score that I'm using, I would instead look at the areas. And I'd look for an area that matches the area that I'm looking for. So in this case, I'd be looking for 0.25. Now I do have to be careful because remember, the z-score table is the area between the mean and the specified z-score. So if I'm looking for this z-score, the area in the z-score table is actually this area, not that area. So how much is this area? Well, remember that if I'm working with 1/2 of my normal distribution, then the total area here is 0.5. If I'm splitting this up into a section that's 25% or 0.25 on the left side, then what's on the right side? Well, 0.25 plus 0.25 gives me 0.5. So in this case, this is a kind of a special case where I'm looking for the exact same amount. I'm still actually going to be looking for 0.25. So that means I'm going to come up to my z-score table and look for an area that's 0.25. Now you'll notice right here, I get pretty darn close. I end up with 0.2486 and 0.2517. So which one do I pick? Because neither of them are exactly 0.25. Well, what I'm going to do is I'm just going to pick the one that's closer. And in this case, 0.2486 is closer to 0.25. So I'm going to pick that one. So what that does is that gives me a z-score of 0.67. So the 25th percentile corresponds to a z-score of 0.67. And then if you have a specific data set, you can use that to calculate what your data value would actually be for a z-score of 0.67. So that's how percentiles work. It's asking the question what data value or what z-score will result in you having an area of 0.25 or 0.1 or whatever percent you're actually looking for to the left of that value. So with that in mind, let me ask you this question. What's the 50th percentile? Well, this is asking the question, what data value will give you 50% of your data to the left of it? And if we understand normal distributions correctly, we can understand that this actually ends up being the mean. The mean is always your 50th percentile because the mean will split your data exactly in half. Okay, well, a lot of scattered concepts here that we were working with today. We talked about percentiles. We talked about how to actually calculate areas for normal distribution. We have to use z-scores and we have to use this z-score table in order to be able to actually do it. And then we also talked about how to find means and standard deviations using integration for non-normal probability density functions. So go ahead and get started on the homework, and we'll be going through 3 example problems in the example video. So once you get stuck, go check out the examples video, and we can look through some of those. Good luck, and I'll see you in the next video.